The physics of electromagnetism. This video is an overview of a course on the physics of electromagnetism, which is the theory that unifies electricity and magnetism. No doubt you're familiar with at least some aspects of electricity and magnetism. Historically, they were studied separately in the past. Both of these phenomena are known for their ability to exert forces on objects at a distance, or a non-contact force. As far back as the ancient Greeks, they were familiar with the fact that amber, if you rubbed amber, you could attract small bits of stuff to it. As a matter of fact, the Greek word for amber is electron. That's key to the electricity that we study today in electric circuits. It's also key to how an atom is composed. They also found that if this rock or lodestone, which is actually a magnetic form of magnetite, a natural iron oxide, if it would attract other pieces of metal or other lodestone to it. So again, these forces, these actions at a distance, have been linked to both electricity and magnetism. If we see here that this is called the amber effect. If you've ever rubbed a balloon in your hair, then you can get the balloon to stick to the wall, or you could get it to two balloons to repel each other. So we can get either attractive forces or repelling forces. Most young children have also played with magnets. If you put poles will repel each other or push away, and unlike poles will attract each other or get connected. We make very strong magnets today. It can be very difficult to separate a north pole from a south pole. So static electricity and static magnetism can be still studied separately. They are both exerting these forces at a distance where matter is not interacting with other matter. What is it in fact interacting with? The study of this started back with Wilbur Gilbert in the 1600s, where giving the rise to field theory, where matter is interacting with a field in the space surrounding it and results in these non-contact pull or push forces. And we see here the Earth and a drawing of its magnetic field lines, always forming closed loops. This is also a magnet, which is similar to what we would get if we saw an electric dipole. So if we stop for a moment and pause the video, just make a list of everything you already know about electricity and magnetism. When you're done with that, we can come back and we'll talk more about electricity and magnetism separately and the rise of. Well, hopefully you came up with a great list of what you know about electricity and magnetism. Now let's go through a little bit more history. As we've stated, originally they were studied separately until famously in 1820, Hans Christian Ørsted is credited for the discovery that electric current in a wire could deflect a compass needle. Well, historically, the ancient Chinese were able to float magnetite on water and found that it would line up with the Earth's magnetic field. If you remember, magnetite is a form of a magnet. So we have this magnetite floating on water, low friction, acting like a compass. And that Earth's magnetic field being able to affect that compass. Well, now Hans Christian Ørsted discovers that electric current can also affect that compass. So our electric current in the wire is doing what the Earth's magnetic field can also do. So that tells us perhaps that that current in a wire, that electron that's moving through the wire, we said that electricity is associated with a field, so we'll associate that with an electric field. This electric field, or charge moving through a wire, is then creating a magnetic field so it can affect a compass needle. So a moving charge is creating a magnetic field. Well, is it true then that a moving magnetic field can then create a current and move an electric charge? And that was discovered in 1831 by Michael Faraday. Again, experimentally, he was a great experimenter, proved that a moving magnet could make a current flow. Ironically, it was also discovered by Joseph Henry, an American, in 1830, but since he didn't document it well, Michael Faraday is given the credit for that. So now we have electric field creating a magnetic field, a magnetic field creating an electric field. It does require movement or some mechanical force. So this huge effect on today's society. This is how we're able to you create generators to create electricity. You use electricity, then electric motor, to create work, mechanical work. So that was in 1831 that we discovered that those two are related. 1820 and 1831, that electric and magnetic fields are related. And in 1873, Maxwell, the great mathematician, his treatise to electricity and magnetism, mathematically unified the electric fields and magnetic fields into one unified theory of electromagnetism. So electromagnetic force is one of the four fundamental forces of physics. If we consider electromagnetic force to have a strength of 1, then gravity has a strength of 10 to the negative 45. If we just take these four forces right now and just look at gravitational force and electromagnetic force, they have a lot of similarities. We're actually quite familiar with, or have a lot of experience with, gravitational force. It's what holds us to the earth. It will also attracts masses together. It's just an attractive force between masses. Electromagnetic force is an attractive or repulsive force between electrically charged particles, and it's responsible for holding atoms together. So that's on two ends of the spectrum, electromagnetic force and gravitational force. We also have our strong nuclear force. If the electromagnetic force has a strength of 1, strong nuclear force has a strength of 100. That's what's holding the nucleus of our atoms together, the force between the nucleons and the quarks, or the protons and the neutrons in classical physics. Our weak nuclear force, still much stronger than gravity, but weaker than our electromagnetic force, that's what's responsible for our controlled beta decay, or the release of radioactive beta particles from our atoms. So let's outline this course. We'll start by looking at static electricity. That includes electric charge, electric fields, electric energy, and electric potential. And then we'll look at capacitors, something that we use to store electric energy and static by storing static charge on conductive plates. Then we'll change to dynamic electricity, and we'll look at currents in a wire primarily, but this could also include any currents. We'll look at resistance of materials, and then we'll also do some looking at circuits, and we'll look at circuits with resistances and capacitances. And then we'll bring in magnetism. So magnetism now, we're going to be looking at magnetic field. We'll look at electromagnets, how current can create a magnet, or current can create a magnetic field. A moving charge can create a magnetic field. And then we'll look at electromagnetic induction, how a moving magnet or a changing magnetic field can create an electric current. So now we have electromagnetism. We also have inductors. So we'll use inductors in our circuits also now with resistors and capacitors that we've studied before. We'll also look at electric motors and generators, electric transformers, and then we'll start studying electromagnetic waves and how we carry radio waves and light waves. So that's what this course is going to entail. Again, what you want to do before you start to take the course is brainstorm. If you're in class now, brainstorm as a group. What do you already know about these fundamental subjects that we're going to study in this class? It's good to think about what you already know. Some of it may be true, and some of what you learn may surprise you. So I'll see you in class.